Am I back?
Yeah.
Yes.
Not a good day to freeze. Sorry, guys. I have to run around trying to figure out what's wrong. Okay, let me share my screen again and pick up where I left off here. Let's see if I can do that. All right, let's see. Okay, all right. So I don't know where I froze. You know the song that's so popular, that Frozen, that all the kids run around singing and everything. It's got totally new meaning for me because my other calculus class said, while you were gone, we sang the song Frozen. And I'm like, okay, whatever. So here's what I'm doing on this one, guys. I took the antiderivative. I plug in the upper limit first, and then I plug in the lower limit. So when I plug in the lower limit, it'll be 1 to the 4th over 2 minus 1 squared over 2 plus 1. After that, it's just grind it out. This is 81 halves right here minus 9 halves plus 3. If I shoot the negative through here, it'll be minus a half. Minus a minus will be plus a half. Minus 1. You can do that on the calculator, but what it ends up being, let's see, 81 minus 9 is 74. I think that's 37 plus 3 is 40 minus 1. Maybe I get, let's see, what did I say that was? 74. That's 37 plus 3. 40 minus 1 is 39. I felt like I saw 38, but 39. Anyway, you plug it in and you compute it, okay?
Oh, yeah. I got 159.5.
Yeah, something went wrong in yours, Haley, and I couldn't quite find it when I was looking at it, okay? All right, so everybody okay with that? So you're just, this definite integral thing is just finding the antiderivative like we've been doing and then plugging in these numbers that are on here. They call the limits of integration. Now, where do we use it? 2 places. I've really only had a couple of applications. I did, by the way, put a few extra. I had an extra quiz in the homework. I mean, in the Moodle section. I had hidden it from you guys because I was afraid I don't want you to get overwhelmed by all the stuff that was there. But this is what it looked like. So let's make sure everybody understands where we plug things in and what we do for these definite integrals, because there'll be a few of these to do, and they should be easy. I won't even play out the numbers, but I'll just do what we have to do. First thing we do is take an antiderivative. So that's going to be 3x cubed over 3, which we're going to evaluate from 1 to 3. You can simplify it. It's x cubed from 1 to 3. You'll plug the 3 in first, and then subtract the 1 plugged in, which will be, in this case, 27 minus 1, or 26. So antiderivative, plug in the top, take away the bottom plugged in, with the number plugged in. This one right here, the antiderivative is 3x squared over 2 plus 2x. I'm going from 0 to 2. My next step is just to plug in the 2 everywhere. And then I'll subtract, please, 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 please don't make me take off points for missed signs here, minus parentheses. But this is an easy one, because if you plug in 0 to any of these, you're just going to get 0. So you wind up here with 6 plus 4, or 10, I think. You just do those numbers. Finally, if you do this one, I wanted to do this one because it was a fractional power. We still just add 1. We want to find the antiderivative, it'll be minus a half plus 1 over minus a half plus 1. I'm going to evaluate from 1 to 4, but I need to clean it up before I start putting stuff in, guys. 1 minus a half is a half, so that's x to the 1/2. Minus a half is a half. I'm going from 1 to 4. If I invert and multiply, this is 2. X to the 1/2 is the square root of x. I'm going to rewrite it because I think that makes it easier for me to plug things in. If I go backwards and rewrite it. Plug in the upper limit first. Plug in the lower limit last.
What about the over 1/2?
Well, I inverted and multiplied by Haley. I went, so
Okay.
that's where that 2 came from right there.
All right.
Got it? Okay. So that's going to be 2 times 2 is 4 minus 2. I wind up with 2 there. So square root of 4 is 2. 2 2s is 4 minus 2 is 2. We had a couple of applications. I'm gonna do one right here, and then I'm gonna go back to one of the business applications. Because this is all we have done with this definite integral. Okay. We mentioned yesterday, I guess it was yesterday, that it was area under a curve. So if you see a shaded region like this, and you're asked to find the area under that curve, and there are places if you're econ or a business major, you'll need to do that. Otherwise, you may not. But that's the integral from 1 to 8, because we're bounding the region off on the left and the right by those 2 lines. And the area under the curve itself, we'll put the x cubed there. So if we wanted to know what that area was, that's one of the applications of these definite integrals. And it's pretty easy, okay? I'll anti-differentiate it. I'll evaluate it from 1 to 8. It'll be 8 to the 4th over 4 minus 1 to the 4th over 4. And I don't know what that is. We'll just call it, we'll do it on your calculator. It's just some number, okay? Square units. All right, I'm going to go back and do one more like this that was actually on the sample test. And then I'll start from the beginning of the sample test to look at the rest of the stuff, okay? I sort of want to take care of this stuff at the tail end, so I made sure everybody's seen that. All right, I'm going to do one more like that. Okay, at the tail end of the sample test, there was this problem right here. It was number 9. And number 9 said, whoops, somebody's trying to get in. I guess either somebody got bumped or, oh, there's Stephanie. Okay. Okay. So, so this, still having trouble getting in. Hang on. All right, there we go. This definite integral, the thing with the 10 and the 20 on it, this was number 11 on the sample test that I gave you. It says the marginal cost of serving additional clients at a law firm is given by C prime of X. What's the total change in cost if the firm goes from serving 10 clients to 20 clients? Okay. Now, guys, I'll emphasize again, if you say you're given a derivative and you're asked something about, you give them, like here, you're given the derivative of cost and you're asked to find something about the cost. You got the derivative, you want to find something about the cost, you need to take the antiderivative. So that's what I did. I took the to find this cost function right here, this change in cost. All right, this is this net change in cost. I'm first going to take the antiderivative of that marginal cost right there. We know how to do that. It's just the power rule by the integral of any constant is that constant times x. Notice you can check because its derivative is the derivative of this is 675. If you take the antiderivative of 0.5x, it'll be 0.5x squared over 2 because you're adding 1 to that power right there. You're adding 1 plus 1 is that 2, and then that other 2 down there. If you want to know the net change, it's sort of like finding the area under a curve. What's the increase in your cost? You've got now a cost function. You want to evaluate it from 10 to 20, which means I'm going to plug in the 20 at the top first. So that one always goes in first in this definite integral. So that's 675 times 20 plus 0.5 times 20 squared. I mean, it's going in for x. Divided by 2. And then subtract off 10 plugged in, minus parentheses. Okay. I feel like I'll be begging till the day I die for people to put parentheses in places. Or that'll be what I'm babbling about when I have dementia when I'm 90 something. If I plug in 10, I have 675 times 10 plus 0.5 times 10 squared. I just plugged it in right there. I'm plugging in the 10. When I take everything away, $12,900 or whatever. That's their additional cost for serving 10 more clients. Just why lawyers charge a lot of money, because it costs them a lot to do research. They pay somebody else to do the research. Okay. Question about that. I did do one more here, guys, that I'll set it up so you guys know, so it'll look, those two applications of this definite integral. I had asked you, this is a new problem. I put it on the tail end of this thing when I was putting it in the computer. If I want to find that shaded area right there, the area that's shaded goes from 0 to 2. So I'll take this integral from 0 to 2 of the curve, and the curve is this thing, this curve that's on top of this region right here. So I'm trying to find the area of that region. It's pretty simple. You integrate it from what the x values ranged from here, and the integral of 4x cubed is 4x to the 4th over 4. The 4's will cancel. Upper limit in first. So you see it's actually going to end up being equal x to the 4th from 0 to 2. Upper limit goes in first. Lower limit goes in last. We end up with 16 square units. I didn't tell you if it's in inches or feet or whatever, but if it's area, it's square units. All right, questions on any of that last piece? Otherwise, I'm going to go down and do start with this thing from the beginning, where this test starts. Are we okay with this? Okay. All right, let's look at the beginning. We started this section with just these things called exponential functions. First thing I talked about was how do you graph them? Well, basically, you can put them in your calculator and get a picture, get a look at the graph. This would be 2 to the exponent minus x. Or we can plug in our own points. Probably what I'll probably do is something similar to this, and I'll say graph this picture if you evaluate at these points. So that's all I've done here. For example, and I think I've done it wrong. Hang on, let me just, don't even look at that. Hang on a second. I did something back. I did something backwards.
I was about to say, I had a question because I thought like negative times a negative would be a...
It is. It's backwards. Okay, don't forget it. You never saw it, okay? So if I plug in -1 here, minus a -1, that'll give me a 2 right there. So again, that's 2 to the -1, which is 2 to the 1st. If I plug in -2, it'll be minus a -2, and 2 squared is 4. Minus a -3 will be 2 cubed, that's 8. Anything to the 0 power is 1. And then if I plug in 1, it'll be 2 to the -1. Now, guys, 2 to the -1, as we know, because of that's a negative power, is the same as 1 over 2 to the 1st. So that's 1/2. 2 to the -2 would be 1 over 2 squared, which would be a 4th. And 2 to the -3 would be 1 over 2 cubed, which would be an 1/8. So I've got those values, and I'll just put them on the graph. At -1, it's at 2. At 1, it's at 0. At -2, it's up here at 4. At -3, it's up at 8. At 1, it's at 1/2. I can't even, my graph isn't even good enough, but basically what this thing is doing is just getting close, smaller and smaller fraction, just to getting closer and closer there. That's a horrible picture. But going down this way, it goes through 0, 1. Let me get rid of this. Okay, let's try again. I at least want to try to make it, doesn't have that much wiggle in it, guys, but it looks like that. What's the domain of this function? I mean, you can keep plugging in things, they get smaller and smaller this way. You can keep plugging in things, they get there, it jumps up, keeps going up and up and up. The domain on a function like this is -infinity to infinity, okay? You can tell that it is not increasing. It was when I got it wrong, but it's decreasing, obviously, because if I go from left to right, the y values are falling. Is it concave up or concave down? Anybody?
Yeah.
It's concave. Hold water or dump water?
Hold.
Hold water, so it's concave up. Okay. So we started off with those exponential functions, and then we tried to figure out how to use the calculator with it. And that's what this next problem's about. Can you use the calculator? This is just an exponential function where your exponent is t maybe instead of x. It says it's going to be the population in the US from the year 2000 in millions. That's about right, guys. Now our population is about 350 million.
Well, why did you put a dollar sign?
I don't know. Because right now people are worth money. I don't know. Okay. If you're alive, you're worth something. God, I don't know. It's scary.
Funny.
But anyway. All right, so guys, all I did was say, okay, the year 2000 is times 0, 2020 is times 20. Estimate the population in 2019. All I did, and remember, you don't put in 2019 up there because we said t equals 0 is going to be 2000, 2020 is going to be 20, so 2019 is going to be 19. I put that in there, and that's the population. People, okay, not dollars, in people. Sorry. Does everybody feel okay about using your calculator? It's just, I would just put this one in mind. It depends on what your calculator looks like, but 1.01. Sometimes some people have a box to put their exponent in. Some people have a cursor, but anyway, it's just 19. It just looks like that. Okay. All right, this next one is another indication of whether you can use your calculator properly or not. It says the population of a bacterial culture is modeled by N of t is 925 over 1 plus e to the minus 0.3t. This is when we started talking about this very special exponential function, not just 2 to the t or 5 to the t, but this e to the t. It says, what's the population on day 5? So you got these bacteria multiplying, dividing and multiplying and dividing and multiplying. All we need to do is put the t equal 5 in here. You have to be a little careful. You got to make sure you're going to have, when you put in your calculator, you got to make sure that you've got the 925, and once you write the divide symbol, you definitely want to put parentheses around everything, because if you don't, it's only going to divide by the first thing you wrote there, and the rest of it's just going to add on to it. You've got to put parentheses around the whole thing. So I put in 1 plus, and then remember the e is second ln. Make sure you see that e come up, minus 0.35. Now, it's easy on the calculator to get this wrong. This is a minus sign, not a subtraction. If you were to put a subtraction in there, it would say error. And if you write, it'll give you quit or go to. If you go to it, what you almost always see in this case is that you put the subtraction instead of the negative sign there. I got 756, and I approximated it. It had a little decimal value here, but since we don't talk about a partial bacteria, it's like people, we don't talk about 3.5 people. I just rounded it to the nearest whole number, and I got 756 in there. Everybody feel okay about using the exponential stuff on this? Are you okay with that? All right. Okay. Next thing we did was say, okay, there's some really important applications of this exponential function. And this did have to do with money and compound interest. And what we said was, we start out with what's called the general compound interest formula. It looks like that, where P is the amount of money that you put into the bank to begin with, R is the interest rate in decimal form. Listen to me, guys, because if I say 3%, you need to put 0.03 there. If you put a 3 up there, you're getting an interest rate of 300%. And you need to write me and tell me what planet that's on, because I need to go make a little money and come back to Earth, okay? Write, when it's 3%, write 0.03. Okay, N stands for the number of compoundings per year. T stands for the years. So first problem, suppose you have $1,500 to put in a savings account that pays 3% compounded monthly. How much will you have after 10 years? Original amount's $1,500, that's my P. 1 plus 0.03 is my interest rate, so there's my R. I'm compounding monthly, that means 12 times a year. And then this is the number of times you get to compound. Well, if you do it 12 times a year for 10 years, you just need to multiply there. That's gonna be 120. I wound up with 2024.03. 2024 03. Okay. Interesting thing about interest rates right now. I had some CDs at a credit union, and I was trying to be safe with some money, which was actually turned out to be a good idea. And the interest rate was about 2.5%. Now that the government is trying to alleviate the issues economic issues caused by the coronavirus, they have dumped interest rates down to 0% technically, and that 0% indicates how much the government has to pay back, interest they have to pay back, which is basically none. So we're saving a lot on the national debt because we're down to 0. But if you look at a savings account where you had money at 2.5%, at the next time you look at it, it'll be like 0.5% or something like that. They're going to pay you virtually nothing on your money, which means you can't stay ahead of inflation, if there is any inflation, which there is. If you want any hamburger now, you're going to go to the grocery store and you're going to pay $9 a pound for it instead of whatever, $3 a pound, whatever it costs. Okay, so what we've got here. Next thing, we said that if you let, right here, if you let this number of compoundings get bigger and bigger, like monthly, every week, every 2 seconds, then what happened is that you were taking a limit as the number of compoundings went to infinity, and it turned out to have something to do with this exponential function. That kind of compound is called continuous compounding. It's the best you can do. So suppose you have that same $1,500 to put in a savings account that pays 3% compounded continuously. How much will you have after 10 years? All you have to do with this formula is put in your original amount, put in your 3% right there, and put in the years. That's all you have to do. You have to have the percentage rate, the years, and the amount you start with. And you get 2024.79. That is not a lot more than you had doing it monthly, but that's because the interest rate is kind of low, and it's 10 years. 10 years seems like a long time, but maybe not, I don't know. But that's what I got when I computed that. All right. You look at this last one, a little bit different question. It says, suppose you found an account that pays 8% compounded continuously. That tells me that I'm going to be using this formula right here. That's the continuous compounding formula. You see that compounded continuously, you're going to be using that E formula. So it says, if you would like to have $2,000 after 4 years, how much would you need to put in the bank now? So they're shifting things up on me. They're giving me the amount that I want after 10 years and asking me to find what I have to put in now. This is the now. The P is the now. The 2,000 is later. And I want to have that $2,000 later. And the P is now. So they're saying, okay, if it's 8% and you're going to do this for 4 years, how much would you have to put in right now to have that 2,000? So in this case, guys, the P is your variable. So I've got 2,000 is P e to the 0.32. Easy problem. Divide by e to the 0.32. And it'll isolate P. And 2,000 over e to the 0.32 I got was 1,452.30. So that's called a present value. What do I need? What's the value of money in the future? If how much money right now would be worth $2,000 is what we're saying in this 4 years from now at 8% interest. Okay. Okay. If you wanted a formula for that, I could isolate P if I just looked at a generic formula and I divided both sides of this thing by P, by e to the RT, P would be equal to A over e to the RT. And that's just, this way you only have to remember one formula, but if you just isolate P, that's what you're getting. And that's what I did. All right, I took the 2,000 over e to the rate times the time. Is everybody okay with that stuff? The next thing we did was talk about, well, what's the derivative of an exponential function? Now let's back up for a minute and talk about derivatives in general.
Yeah, can we really talk about these? Because I'm so focused on doing antiderivatives.
I know. Yes.
I get confused switching back and forth, and I forgot what to do.
And guys, when that's true, and that's going to happen on this test, because sometimes you're going to be taking the derivative, sometimes you're going to be taking the antiderivative. So the only new derivative we had was this exponential thing, and we have quotient rule, product rule to go along with it. Okay. So one thing you might want to do on this test, you're maybe at the top of your mind is antiderivatives. Go through and do the things you have to do antiderivatives for, and say, okay, I've done all the antiderivatives, and then go back and do the derivatives so you don't get mixed up between the two. But that being said, we only have one new rule, and we know derivatives are the same things. They're rates of changes. They're slopes of tangent lines to curves. One of our quizzes had that on it. I didn't put this, but it's fair game, okay? And we had what's the rate of change, what's the slope of the tangent line to the curve, that kind of thing. But what you're doing on a problem like this is using a new rule. And the new rule that we picked up was that if f of x is e to the g of x, f prime of x just repeats itself and multiplies by the derivative of the power. In other words, that thing right there is the derivative. See that? And the thing that's also a little bit, no, never mind, I'm not going to say that. Never mind. Okay, look at number 1. I want to know the derivative of 6 e to the 7x. Well, you just write the 6 down. That's just a constant. The derivative of a constant times a function is the constant times the derivative of the function, okay? So really what I'm asked to do here is differentiate e to the 7x. E to the 7x, here's what the rule says. It says repeat it. So I repeated e to the 7x. Why in the heck that turned into a 3, I have no idea. Let me get it back right here. That's a 7. Sorry. It repeats itself. Man, where was I when I was doing, what was I doing here? Okay. I want you to see that. It repeats itself. Now, what's the derivative of 7x?
7.
7. So that's what you put there. If you play it on out, 6 times 7 is 42. So the answer is 42 e to the 7x. 42 e to the 7x. Okay. All right, let's look at this next one. This is 3 different terms. The last 2 are easy. The derivative of 2x squared, bring down the 2, it's 4x. Now, here's what Haley's talking about, though, guys. You've been doing antiderivatives so long, you might think, oh, I add 1 and put it over that. No, that's for an antiderivative. We're taking a derivative here. So it's our original power rule. Bring down the 2. 2 times 2 is 4. Take away 1 is x to the first. And the derivative of a constant is 0.
So now, you just left the 3e to the x?
Yeah, here's why. Because number 1, 3 is a constant, so I just go ahead and write it down. E to the x repeats itself. And what's the derivative of x, guys? What's the derivative of 1x? What's the derivative of 1x? It's just 1. So if it's just a plain old e to the x, where'd it go? If it's just a plain old e to the x, I'm really just multiplying by 1, which I don't need to change, don't need to do anything. So if you want to think about it this way, you've got, if you have f of x equal e to the x, if it's just that function or just a constant times the function, then f prime of x is itself. It repeats itself. But actually, what happens here is that this is the generic, and it works because you multiply by the derivative of whatever this power is. Well, the derivative of x is just 1. So that's how I get that.
Can you explain 2x squared again to make sure that I have this right?
What's the derivative? Remember the last test when we were finding all the critical numbers and all that stuff? That's what you're doing now. You're taking the derivative, Stephanie. So when you're taking the derivative, you bring down the power, multiply, and then take away 1. Okay. So it's 2 times 2, x to the 2 minus 1. Versus an antiderivative where you add 1 and put it over that. It's an inverse operation, but that's just a plain old derivative right there, okay?
Okay.
You okay? Sure?
Yeah, I got it.
Okay. All right, so in the end, and the derivative of minus 3 is 0. Okay, let me ask you something. The derivative of minus 3 is 0. What's the antiderivative of minus 3? The derivative
Minus
of a constant is 0.
X.
The antiderivative is minus 3x. So you're going back. So you got to just be careful. All right, let's look at the next one. This next one, be careful here. You may not see it. You may just sort of be stuck seeing one thing, but you really got two things there. This function times that function. Those are two functions, guys. They're two individual functions. In order to differentiate two different functions, you need the product rule. First, I'll call this my first. I'll call this my second, okay? It's going to be first times the derivative of the second. Okay, let's look at that. What did we say the derivative of e to the something was? It repeated itself. See how I repeated it right here? It repeated itself, and then it multiplied by the derivative of its power. What's the derivative of its power here, guys? Derivative now. What's the derivative of the power there?
4x cubed.
Yep,
4x.
4x cubed. Yep, it's 4x cubed, right. Plus the second, didn't change it, times the derivative of the first. And the derivative of the first is 3x squared. Okay, so that's the product rule. This one right here, this last one here is pretty obvious. It's a quotient. You got that quotient rule is messy. But remember, it's low D high minus high D low over low low. What that means is you take the bottom, this one, and just write it down, times the derivative of the top. Well, the derivative of 2x squared is 4x, minus the top, which is just 2x squared, times the derivative of the bottom. Now, these are two different terms.
Did she freeze again?
Oh, man.
I think she did.
Oh my lord.
Hang on. I'm coming back. Shit.